Now it's a time to start a new chapter, that is current electricity. Now you have studied electrostatics, electrostatic potential and capacitance till now. I hope you have the basic idea that how to study the charges at rest. Either they are bound or they are free. So ultimately till now we have studied about all parameters of charges at rest. Now it's a turn to understand when charges start to move, what is going to happen. So basically this chapter is going to talk about the dynamics of the charges, that is the motion of charge particle inside a material, or we can say we are going to study the concept of current. So in this chapter we are going to see the heating effects of current, basic parameters of the current and the dependence of resistance and the material properties on the flow of current. So let's start our topic and let's try to introduce what current is and how we are going to define it. Now electric current, here we are discussing an electric current. So I have taken a material and in that material I have taken an area of cross section A. Now let's suppose we have taken a situation in which some positive charge is moving through this area from left to right, and in the same time frame negative charge, that is Q negative, is moving from right side to the left side of this area. So if I ask you a simple question, what is the net positive charge which is flowing through the area from left to right? I hope this idea must be very clear to you that whenever a negative charge is moving from right to left, it is actually the equivalent amount of positive charge which has moved from left to right. I hope this idea is very clear to you. So if I want to write out the net positive charge flowing through the area in the interval t from left to right, then it would be Q is equal to Q positive negative Q minus. Why there is a negative in the front of Q negative? Because Q negative would be negative charge, and since the flow of negative charge in the opposite direction is equal to the flow of positive charge in the opposite direction, so I have taken this expression. So Q is equal to Q positive minus Q negative. I hope this is very clear to you. If I see the further discussion of the current, now current is basically defined as the rate of flow of charges, or we can say rate of flow of charges across an area. But current does not depend upon the area. Current is independent of area, but whenever the charge is flowing, we need to specify the area through which the charges are flowing. So for this area, then Q amount of charge has flown through it in a certain time t. So obviously current is being defined as charge flown divided by t, and clearly you can see charge has a unit of coulomb, time has a unit of second, and coulomb per second is given a new unit that is called ampere. So current has a SI unit of ampere. So we can define it over here. Electric current through an area is the rate of transfer of charge from one side of the area to the another. I hope this is very clear to you. Now we have many situations as per the questions. In some times positive charges are moving, in some questions only negative charges are moving, and in some questions both positive and negative charges move. So how you are going to decide a direction associated with the current? So how you are going to say current is flowing in right to left or left to right? So conventionally the direction of current is taken as the direction of flow of positive charges only. See, all the current or the I factor which we are going to use in our further complete chapter, the direction is actually because of the direction of flow of positive charges only. But if in some question, let's suppose direction of flow of electrons is given to you, so what you are going to do? Obviously the direction of flow of electron would be opposite to the direction of flow of positive charges. So conventionally it is always taken that conventional direction of current is always opposite to the direction of electronic current. I hope this is very clear to you. So it doesn't matter which charge is flowing in the system, you should able to find out the direction in which the same effect would happen if positive charge would have moved, and in that direction there would be current. I hope this is very clear to you. So I hope the direction and the basic idea of the current is very clear to you. Now we need to understand some important parameter or types of current. So the first category is the average amount of current flowing through an area. So what is this defined? If delta Q charge flows through any cross section of conductor in the interval starting from t to t plus delta t, then average current in that interval is defined as the ratio of delta Q to delta T. So you can clearly see Average current is the ratio of delta Q is the amount of charge, delta T is the time taken by the charges to flow from one end of the area to the another end. I hope this is very clear to you. And as I have just discussed that coulomb per second is defined as ampere, so SI unit of current is ampere. And if I talk about the dimension, that you must know that in the 7 fundamental units you have described in the first chapter, unit and measurement, current is also one of them. So the dimension associated with the physical quantity current is A. So the dimensions of current is A to the power 1 put in the square bracket. I hope this is very clear to you. Now let's move ahead and see what happens if this delta T time reduces to a very less time. What happens is we need to find out the instantaneous amount of current. So in the limit of delta T tending to 0, the current is defined to be the instantaneous current at time T. So what we can see, if I limit delta T tends to 0, delta Q by delta T, I'll get d by dt of Q. That means current is defined as the rate of change of charge. I hope this idea is very clear to you. Now, that's clear that how to find the current if the charge function is given to us. But in some situation what can happen is, if I reshuffle this expression a little bit, then I dq, I dt is simply equal to dq, and if I integrate it up, then I am going to get the total charge which has flown in the circuit from T initial to T final, and this is 0 to Q. I hope this is very clear to you. So what is going to happen in that scenario? Let's see that. Let's suppose we need to find the total charge flown in the interval in the time t1 to t2. So if I draw a graph between current versus time, let's suppose this is the graph, and these are the different zones of t1 and t2. I hope this is very clear to you. Now in this diagram, clearly this point is t and this point is t2. Now what we need to do is we need to find out the total charge which has flown in the circuit in this given interval. Now clearly from the previous knowledge we know that Q is given as integration t1 to t2 I dt. So in any question, let's suppose the function of I is given to you, and function of I is given as a function of time obviously, then that current function can be integrated under those limit t1 to t2 to get out the charge. But there is one more application to the definite integral. Even if the function of this current is not given to you, what you can do simply is we can find out the area between the current and the time courses curve in the interval t1 to t2. So this shaded region is actually the area, and this area would be equal to the charge flown through the circuit in the given time interval. And we know whenever we have the charge which is flown through the circuit, I can simply find out the average current. So average current would be simply charge divided by time interval. So charge would be given either by the definite integral or by the area below I versus t graph divided by the time interval. I hope this idea is very clear to you. So for the better understanding of these concepts, let's try to solve some questions and add to our knowledge. So the question number 1 says 10 to the power 6 positrons are flowing normally through an area in forward direction, and same amount of electrons are flowing in backward direction in the interval of 10 milliseconds. Find the current through the area. So let's try to solve this question. So Q positive is given as per the question. So Q positive is 10 to the power 6 positrons. So obviously the charge on a positron is 1.6 into 10 to the power minus 19 coulomb. So after solving this, this would be 1.6 into 10 to the power minus 13 coulomb. So this is Q positive, which is moving in the forward direction, and the same amount of electron are moving in the backward direction. So obviously Q negative would be 10 to the power 6 into negative 1.6 into 10 to the power minus 19 coulomb, because charge on an electron is negative. So this would be negative 1.6 into 10 to the power minus 13 coulomb. Now what is going to happen? We have the expression for current. Current is given by the Q by T. This is equal to Q positive negative Q negative divided by time. So this is actually 1.6 into 10 to the power minus 13 negative of 1.6 into 10 to the power minus 13 and divided by 10 milliseconds. So this is 10 into 10 to the power minus 3. So the current factor will come out to be this negative, and negative will add up. So this is 3.2 into 10 to the power minus 13 divided by 10 into 10 to the power minus 3. So this is 3.2 into 10 to the power minus 11 ampere. I hope the amount of current which is flowing in the question is very clear to you. So let's see another question. Now the next question says, charge through a cross section of a conductor is given by Q is equal to 2t square plus 5t coulomb. Find the current through the conductor at the instant t is equal to 2 seconds. So that is a pretty simple question, because we know that current is simply the rate of change of charge. So we know how to do the derivative of a function if it is given in the terms of time. So this is d by dt of the charge function. So charge function is given as 2t square plus 5t. So we'll have 4t plus 5. So current as a function of time is given as 4t plus 5. Now as per the question, we need to find out the current through the conductor at t is equal to 2 seconds. So let's just substitute that. So current at t is equal to 2 seconds is 4 into 2 plus 5. So 4 to 8, 8 plus 5 is 13 ampere. So the current, or we can say the instantaneous current which is flowing in the circuit at t is equal to 2 seconds is 13 ampere. I hope this question is very clear to you. So let's see one more application of the given formula. If the current flowing through the wire is given as I is equal to 3t square ampere, find the amount of charge that has flown through the wire from t is equal to 2 to t is equal to 5 seconds. So now this is again an application of a simple formula. We know that current is actually the rate of change of charge, and we must be knowing that if I need to find out the charge over here, then I need to integrate from t1 to t2 I dt. And as per the given question, I function is given to us. So this would be integration from t1 is 2, t2 is 5. So this is 3t square dt. So I'll have q is equal to, if I do the integration, then 3 will come out. T square will have an integration t cube by 3. So this would simply be t cube, lower limit 2, upper limit 5. So this is 5 cube minus 2 cube. And we know that 5 cube is 125 and 2 cube is 8. So this is 117 coulomb. So this is the amount of charge which has flown through the circuit in the given time interval. Now if I ask you a simple question that you also need to find out the average current. So the average current for same interval. If we need to find out the average current for the same interval, what we can do over here is, we know that average current, that is I average, is simply charge upon time. So as per the given question, charge which is flown in the circuit is 117 coulomb, time is 5 minus 2. So this is 117 by 3 ampere. I hope this idea is very clear to you, and this you can employ while solving